So let us continue our discussion on the extraction of biomolecules. In the last session, we were discussing about liquid-liquid extraction. Basically, the extraction process is about partitioning of the analyte or the solute molecule between two immiscible or partially miscible phases. Now, what is happening in liquid-liquid extraction? Here, the extraction takes place from one liquid medium to another. That means the solute is partitioning between two immiscible or partially miscible phases. To understand what ratio of the solvents to be used in order to achieve the partitioning of a solute between two immiscible phases. So we had just seen that the ternary phase diagram is used for three-component system. In the last session, we labeled the three-component system as oil, water, and surfactant. Now today we will try to understand how the ternary phase diagram is constructed for the said three-component system, that is oil, water, and surfactant. So the advantage of using such ternary phase diagram, or in short the ternary plot, for depicting the compositions of the solvent systems is that the three variables can be conveniently plotted in a two-dimensional graph. So the three variables what we have chosen to understand the construction of the ternary phase diagram is the oil, the water, and the surfactant. Now the compositions of all the three variables are conveniently or can be conveniently plotted in a two-dimensional graph. So the ternary plots can also be used to create the phase diagrams. That means to create the miscible phase diagram or the immiscible phase diagram. How do they do that? So these plots find application in creating phase diagrams, be it immiscible phase or miscible phase or partially miscible phase, by outlining the composition regions on the plot where different phases exist. So every point on a ternary plot or graph represents a different composition of the three components or the three variables. So each point in the graph represent a different composition of the three variables or components, that is oil, water and surfactant in this example. So there are three common methods used to determine the ratio of the three variables in the compositions. So how to go about it? We'll just see. In the last session, I had asked you people to draw the triangle and the phase diagrams for ternary systems, that is for three component systems, is represented using such a triangle. Now, after drawing this, we had labeled the vertices. So, in the given diagram, every corner of the triangle represents a pure component. We have the label A, B and C. As I said, every corner of the triangle represents a pure component. Now, A represents pure water, B represents pure oil, and C represents pure surfactant. That means A represents 100% of water, B represents 100% of oil, and C represents 100% of surfactant. Right? So the area within this triangular diagram, so whatever the area within this diagram, this represents ternary components. That means all the three variables are falling within this area. Now, what are the rules relating to triangular diagrams? They are as follows. Number one, each of the three corners or vertices, that is vertex A, vertex B and vertex C. So each of the three corners or vertices of this particular triangle represent 100% by weight of one component. Now, in A, it is 100% by weight of water, and in B, it is 100% by weight of oil, and in C, it is 100% by weight of surfactant. So, what does this mean? So, at the same vertex, the other two components represent 0%. Say for example, in vertex A, we have 100% by weight of water, but 0% oil and 0% surfactant. Similarly, in vertex B, we have 100% by weight of oil, 0% water and 0% surfactant. In the same way, in the vertex C, we have 100% surfactant and 0% water and 0% of oil. So, what the things to be remembered over here is the rules to construct the ternary component diagram. We have a triangle and we have three vertices representing the pure form of the component. When I say pure form of the component, we will take it as 100% of that particular component. That means 100% of surfactant alone, 100% of water alone, and 100% of oil alone. When I say 100% of surfactant at point C, that means it doesn't have water mixed with it or oil mixed with it. It is purely 100% of surfactant only. This is true with vertex C. And in vertex A, it is 100% of water only without surfactant or oil present in it. Similarly, in vertex B, it is 100% of oil without surfactant and water. Now, the opposite side of each of the vertices represent 0% of the specific component. That means for the vertex C, where we have 100% of surfactant, the line A, B represent 0% of the surfactant. Here it is, at this point it is 100% of surfactant, and at this point it is 0% of surfactant. Similar to that, we have 100% of water at this point and 0% of water at this point. So the line B and C represent 0% of water. In the same way, the line A and C represent 0% of oil. So in that context, at this point it is 100% of surfactant, and at this point it is 0% of surfactant. If we start drawing the lines with reduction by 10%, we will get the diagram something like this. So this line represents 90% of surfactant. This line represents 80% of surfactant, 70%, 60%, 50%, 40, 30, 20, 10%, and as I said, this line represents 0% of surfactant. And this line represents 90% of water, 80% of water, 70, 60, 50, 40, 30, 20, 10, and this line represents 0% of water. In the same way, these lines represent various percentage of oil starting from 90%, ending in 0% of oil. So the sides of the triangle represent 0% of the three component system. A and C represent 0% of oil, A and B represent 0% of surfactant, B and C represent 0% of water. So the area within the triangle represents all possible combinations of the three component system. So addition of the third component to any two component system will change their solubility. In this example, if you add surfactant as a third component to water and oil, will change their solubility. But at what percentage it changes their solubility is determined using this ternary phase plot or ternary phase diagram. So when a third component such as surfactant in this example is more soluble in either one from the two components, then the solubility of both the components will reduce. That means if it is soluble either in water or if it is soluble either in oil, then the solubility of both the components, that is water and oil, will reduce. But if the third component that is added is soluble in both the components at the same time, that means if C is soluble in water and if C is soluble in oil at the same time, then the solubility between these two components increases. Thus, when surfactant is added to a mixture of water and oil, the solubility of these two components will increase until a point is reached where the homogeneous mixture is obtained or the mixture becomes homogeneous. So this phase diagram is used in formulations of solutions. How to read this diagram? They will take this point as an example. You find the red line, the blue line and the green line. The red line represent water line, the blue line represent surfactant line and the green line represent oil line. At this intersection, what is the composition of the three component system? So to begin with, we'll start from surfactant. This is 100% and this line represents 90%. This line represents 80%, 70%, and here what we are trying to focus, this line, that is blue line, represent 60% of surfactant. Right? So this is the percentage marking for surfactant. This is the percentage marking for oil and this is the percentage marking for water. So considering this, now the blue line is at 60%. That means 60% of the solution is now surfactant. In 100 ml, 60 ml is surfactant. Now, what is the percentage of water? We'll start from here. This is 100% water. This is 90% water line. 80, 70, 60, 50, 40, 30, 20. So the water content here is 20%. So in 100 ml solution, we have 60 ml of surfactant, 20 ml of water. So minus of that gives you the percentage of oil present, but still we'll calculate from the phase diagram. This is 90, 80, 70, 60, 50, 40, 30, 20. This is the intersection which we are focusing. So it is 20% of oil. This is how each point within the phase diagram is read and understood. So if you plot this in a two-dimensional graph, there will be again divisions so that it will be easy for you to mark the percentage of each of the three component system. Clear? Now I said this phase diagram can be used in formulations of solutions. But how it is used in formulations experimentally? So what you do is, this is a hypothetical example for you to understand how the formulations of solutions are done experimentally. We have three columns. The first column represents volume of water with V1. The second column represents volume of oil with V2. And the third column represents volume of surfactant with V3. Now in a test tube, 1 ml of each of water and oil is taken. So you can see two distinct layers, which is an indicative of two-phase system. If you take 1 ml of water and 1 ml of oil in a test tube, you can see that it is an indicative of two-phase system. Two distinct layers can be seen. Now when surfactant is added from the burette to the mixture of water and oil, it is added till homogeneous single phase system is obtained. So you keep adding, because this surfactant reduces the surface tension, and at certain point, as I said, the mixture becomes homogeneous. So you keep adding the surfactant till the mixture becomes homogeneous. Now repeat the experiment with different volumes of water, keeping the volume of oil as constant, or it is either way. You can keep the volume of water constant and you can change the volume of oil. And you keep adding the surfactant. For each of the experiment, there will be consumption of different volume of surfactant in order to reach a homogeneous solution phase. So for example, if you take 4 ml of water in a test tube and 1 ml of oil, in order to obtain a homogeneous mixture, you need to add about 2.5 ml of surfactant. So you continue the experiments for several volumes of water if you are keeping the volume of oil as constant, or vice versa. And from these values, what you have obtained, you have to calculate the respective percentages of water as well as oil and surfactant. Now, how do you calculate the percentage of the components, the percentage of water, oil, or the surfactant? You have the volumes of the three component system, and you need density of the three component system. Here the density of pure water is represented by the formula W1 for easy understanding. That means W1 represent density of the water, W2 represent density of oil. I have taken sunflower oil as an example because I have to show the density of oil. So I have taken a specific example of sunflower. And W3 represent the density of surfactant. I have taken a cationic surfactant, the CTAC. Now, as per the literature, the densities of W1, W2 and W3 is given over here. So, you have the volume of the three component system. Now, you have the densities of the three component system. And we know that density is given by mass over volume. So, you have the density, you have the volume, so you need to calculate the mass. So, mass is equal to volume times density. So, how do you calculate? I said W1 is equal to, that means for the pure water, what is the volume of the water and what is the density of the. For W2, it is representing sunflower oil. What is the volume of the oil consumed? What is the density of the oil? And for W3, what is the volume of the surfactant consumed and what is the density of the surfactant? Right? Now, how to calculate the percentage of water? Percentage of water is given by this formula. W1 over W1 plus W2 plus W3 times 100. Now, how do you get W1? So, you know the volume of water. Say for example, you have taken 1 ml of water. This becomes 1 times density of water, that is 0.999 gram per ml. So, multiplying that value, the W1 becomes 0.999 over. Similarly, you find out W1, W2 and W3 times 100 gives you percentage of water. Similarly, you have to determine what is the percentage of oil and what is the percentage of surfactant. So, I have used a simple formula to calculate the percentage of all the three components from the available data for the three components, that is, you have the volume, you have the density. So, from the volume and the density, I have determined what is the percentage of the three component system. Accordingly, this is the percentage of the three component system which was calculated for the given set of the data. So, if you take 1 ml of water, 1 ml of oil and 1 ml of surfactant, the percentage calculated for the three component system will be as shown here. Right? So, now you have to plot these percentages in the ternary phase diagram. So, I have replicated the same data over here and I have also replicated the ternary phase diagram which we just saw in the previous slides. Now I'll try to plot these values. So for percentage of water, this reads 33.68. Since it is not a graph sheet, so I'll just plot it for the convenience, maybe somewhere around here, because this is the percentage of water. So this is 0% water line, this is 10% water line, 20% water line, 30% water line, and the value reads 33. So I have taken somewhere like this, around 33, assuming that this is the third division. And the percentage of oil reads 32.67% as per the calculation. So this is 0% oil line, 10, 20, 30, 32. Similarly, we have the surfactant line. This is 0, 10, 20, 30, 32. So this is the water line, this is the oil line, this is the surfactant line. So mark the intersection. Similarly, you plot the intersections for all the other values that you have determined. It will be something like this. Since I have only 6 different values, I could get or could manage to get only these points, but usually you will have the points starting from this line ending with a similar type of plot. It will end up as a curve. So for understanding, I have just used only 6 values and I have tried to plot a curve something like this. This is a hypothetical curve. Now, within this curve, whatever the compositions of the 3 components, all these compositions represent immiscible phases. That means, say for example, this blue line represents 20% of surfactant and the green line represents 30% of oil and red line represent 50% of water. That means water is 50, oil is 30 and surfactant is only 20. So they don't form homogeneous solution. It is immiscible. And anything above or outside this diagram is the composition of the 3 component system, which is miscible. Right? So this is how you chose to understand the exact ratios of the 3 component systems, which makes immiscible and miscible phases, so that it can be easily adopted in order to extract the biomolecules from the solution. So this particular curve or the area, it represents the possible condition of water, oil and surfactant, and the area above the curve, as I said, it represents one phase or the region of miscibility, while that below the curve, falling within this curve, represent two phase or the region of immiscibility system. So how to conclude this? The water, oil and surfactant system in this example is a ternary system with one pair of partially miscible liquid, that is oil and water, and the addition of sufficient amount of surfactant to the oil water system that would produce a single liquid phase in which all the three components are miscible and the mixture is homogeneous. So if you are trying to extract a solute in either water or in oil, you can use these possible combinations. If you want the analyte to be present in homogeneous mixture, you can use any of these possible combinations of the three component system. So this is how it or the diagram distinguishes between the immiscible phase and the miscible phase. Right? So this gives you an idea of what compositions should be used in order to obtain an immiscible solvent system to extract any biomolecule. In this example, it is oil, water and surfactant. Suppose if your biomolecule is in water system, you want to extract it in oil system, then probably you can choose any of the possible combinations. If you forget to fall within this combination and if you choose somewhere here, then it will be a homogeneous mixture and you will not be able to extract the molecule. Right? So this is about liquid-liquid extraction. This is what we saw or discussed in detail about the liquid-liquid extraction. Next, if you have one or more analytes or solutes and you are trying to extract it by partitioning or adsorbing onto a solid phase, then you call it as, or the process is referred to as solid phase extraction, abbreviated as SPE. In the previous extraction procedure, you had two liquid systems which are immiscible or partially miscible. And here in this extraction process, you have the analytes from the liquid sample partitioning and or adsorbing onto a solid phase. So we refer this to as solid phase extraction. Basically, it is a sample preparation technique where we use a solid adsorbent. For example, the octadecyl silanes. And these adsorbents are packed in a device called as cartridges. And the solid phase extraction is used to isolate the analyte in a sample, or maybe even to clean the analyte before going for analysis using HPLC or mass spectrometry. So you have two applications. Number one, the solid phase extraction process is used to isolate the analyte from the sample mixture, or maybe to clean up the sample before proceeding for the analysis using the HPLC or the mass spectrometry. Right? So this is an illustration on how the solid phase extraction take place. As I said, the sorbents are packed into a device called as cartridge. Now this device, or the cartridge what we call in solid phase extraction process, is very much similar to the syringe cartridges, the clinical syringe cartridges which you see in the hospitals. So it is almost similar ones. So here we have the sample reservoir. That means you can add the mixture to the cartridge and it comes and sits in this reservoir, in this space, and the solid sorbent is placed here, and above the solid sorbent and below the solid sorbent you have a porous material which is referred to as fritted disc, so that the sample which is in the liquid form does not straight away disturb the sorbent bed. So there is a fritted disc. The fritted disc looks something like this. This is also porous. Commercially available disc looks like this. So they are placed here. So what happens is they are porous. So the sample pass through this disc. If there are any extraneous material, so the disc actually prevents the extraneous material from passing through, and only the analyte solution passes through the sorbent. And if there is any other material which needs to be removed, we have a fritted disc at the lower bottom. So you add the mixture of sample, it passes through the fritted disc, through the sorbent, and you can isolate the analyte. This is a generic approach of solid phase extraction. So as the sample is passed through these cartridges, so what is happening here? This is most important component of the cartridge, because you have the sorbent bed. This is only the sample which is present. This is where exactly the separation is happening. You have two approaches that is happening here. Number one, bind and elution. Number two, removal or trapping. Now, this is for your reference how the commercial cartridges look like. As I said, they are very much similar to your clinical syringes. So these are the adapters and these are the cartridges, and here you can easily make out the sorbent bed. So it is tightly packed over here. So these are the empty cartridges, these are the filled up cartridges, and you add the mixture of analyte through these adapters. You can actually pump in or make the analyte mixture to flow through a tubing or something like that. So you have different types of adapters, and the cartridges comes in different sizes also, right? These are all commercially available cartridges. It is the length of the cartridge is also similar to your clinical syringes. Now I said there are two strategies that is happening in the sorbent bed. Number one, bind and elute strategy. Number two, removal or trapping strategy. Now what is bind and elute strategy? This colored image is an interferent. That means we don't want this. This is an extraneous material. And this blue colored and the black colored images are supposed to be the analytes of interest. That means we want these analytes to be separated from these unwanted molecules. So what you do, you add the sample. Now this is the sorbent bed. Now in bind and elute strategy, only the analyte binds to the sorbent bed because of some forces acting between the sorbent material and the analyte molecules. They are all weak forces. And the interferents, since they cannot bind to the sorbent, they are eluted out. Elution means they come out. And later, whatever the analytes that is bound to the sorbent can also be eluted by changing the ionic strength, so that the forces of attraction between the analytes and the sorbent becomes weak, so the analytes come out. So now you have essentially separated the mixture of analytes from the interferents through bind and elute strategy. First is binding, then elution. Now the second strategy is removal or trapping strategy. You can easily make out the difference between the two strategy. In the first, it is binding of the analyte and elution of the analyte, and in the second strategy it is elution of the analyte first, and at the same time the interferents are bound to the sorbents. So here the analytes have no role to play, or they cannot bind to the sorbents. It is only the interferents that bind, and at the same time you are eluting the analytes. The analyte is coming out of the cartridge. So this is removal of analyte, or trapping the interference strategy. Got it? So these are the two important strategy that is used in solid phase extraction. That is bind and elute strategy, where the analyte or the analytes are retained and the analytes are subsequently eluted. In removal or trapping strategy, the analytes are not retained, but they are eluted. Got it? So essentially, if you look at the solid phase extraction, you have adsorption mode, ion exchange mode, and mixed mode. And in adsorption mode, you have normal phase, reverse phase. And in ion exchange mode, you have cation exchange phase and anion exchange phase. And of course, the third one is the mixed mode, which combines the properties of adsorption and hydrogen bonding or ion exchange in one single cartridge itself. It's a combination of all the other two phases. So solid phase extraction is a powerful separation technique for extraction of biomolecules from a mixture of solutions. So in adsorption, you have normal phase and reverse phase, and in ion exchange, you have cation phase and anionic phase. So what is happening in normal adsorption solid extraction? Here the analytes with low to high polarity are separated, and the separation principle is based on polarity, and the adsorbent is non-polar, and least polar compounds elute first. right? So what is happening in a reverse phase adsorption? Here the analytes with moderate to low polarity can be separated. Separation is based on hydrophobicity, and the sample matrix or the adsorbent is more of aqueous, and polar compounds elute first. And in ion exchange mode, we have cation. So the separation is based on charge in both cation and anion with a difference of positive and negative charges. So in mixed mode, I said it is a combination of all the other phases. So understanding the common applications of solid phase extraction, you can see the use of the SPE in pharmaceutical, clinical, diagnostics, environmental, agrochemical industries, etc. To be more specific, in detecting the pharmaceutical compounds and metabolites in biological fluids and drugs in biological fluids, if you want to identify whether the biological fluids has the drugs of abuse, and pollutants, the environmental pollutants, if at all present in drinking water, and what percentage of pollutants are present in wastewater, pesticides, the detection of antibiotics in food and agricultural products or produce. And if you want to remove salts, that means if you want to isolate proteins or peptides, you use buffers. Buffers is a combination of the salts. So at the end of the purification, you want only the proteins or the peptides. You don't want the salts to interfere. So you have to desalt that. Though you have used the buffers in the extraction, you don't want the salts in the buffer to interfere in the purification of the final product. So you have to desalt. So the solid phase extraction cartridges can be used in desalting or separation of lipids, even in water soluble vitamins and fat soluble vitamins too, right? And moving further, if you want to extract, say for example, low molecular weight or intermediate molecular weight compounds such as antibiotics, alkaloids, steroids, so you can use aqueous or non-aqueous solvent systems. And if you are trying to extract the macromolecules, biological macromolecules such as proteins and nucleic acids, you can use aqueous two-phase systems. So I have given you how to draw or conclude the possible combinations to obtain a two-phase system. And when a supercritical fluid is used as an extracting solvent, then it is referred to as supercritical fluid extraction. So these are some of the possible combinations of solvent systems which can be used for extracting the biomolecules. So I'll stop my discussion over here. We can continue our discussion in the next sessions.